Hi dear students, this is me Ishfaq Riaz, and today we are going to discuss an important and interesting topic of gravitation, that is Kepler's laws of planetary motion. Dear students, you already know physics is the study of nature and natural phenomena. Whatever is going on in nature, all these questions are being answered in the science, in the branch of science, that is physics. Now here we are discussing the motion of planets because the laws are Kepler's laws of planetary motion. How this solar system is organized, which force is responsible for the motion of planets around the sun, and how do the planets move around the sun? Are the paths followed by these planets circular or elliptical, and what is the relationship between the time taken by the planet to complete one revolution around the sun and the average distance of the planet from the sun? So all these questions are being answered by the Kepler's laws of planetary motion. But before starting my lecture, before discussing the laws, three laws of the Kepler, let me go into the historical background of the planetary motion. पहले क्या था? Geocentric theory was given by Greek astronomer, that is Ptolemy. Let me write here geocentric theory. Geocentric theory. It was basically given by the Greek astronomer, namely Ptolemy. Right? And he considered, according to this theory, geo means earth and centric means center. According to Ptolemy, it is the earth that is the center of the solar system, and every planet or every other planet, sun including the stars, revolve around the earth. It was first considered by the Greek astronomer Ptolemy. Later on this theory was rejected, and then came the heliocentric theory. Heliocentric theory. It was basically given by Copernicus, an astronomer from Poland. So this heliocentric theory was given by Copernicus in 1543. He rejected basically the geocentric theory, and according to this theory, it is helios means sun and centric means center, and according to this theory given by Copernicus, it is sun and not the earth that is the center of the solar system, and every planet revolves around the sun in definite orbits. And let me tell you one thing about this. Copernicus considered these orbits to be circular, which were later on replaced by this Johannes Kepler. So he considered sun to be the center of the solar system, and every planet revolves around the sun in definite orbits, right? So, and this heliocentric theory, it is the presently accepted theory, and this Copernicus, he was also supported by Galileo. But later in the 16th century, then came the Danish astronomer, namely Tycho Brahe. Tycho Brahe. He studied the motion of the planets for almost 20 years. He observed the motion of the planets and collected some data. But before his death, this Tycho Brahe handed over his collected data to one of his favorite students, जिसकी हम यहाँ पे बात करने जा रहे हैं, that is the Johannes Kepler. He handed over the data to one of his favorite students, Johannes Kepler. German astronomer है ये Johannes Kepler. So what Kepler did, he analyzed the data collected by the Danish astronomer Tycho Brahe about the motion of the planets around the sun, and this Johannes Kepler concluded that the orbits of the planets were not circular as said by the Copernicus, but they were elliptical, and he set forth his discoveries, his conclusions in the form of three empirical laws known as Kepler's laws of planetary motion. ये मैंने आपको historical background बताया about the motion of the planets around the sun. We have 8 planets in our solar system. The sun is the center of the solar system, and this is Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus and Neptune. So all these planets revolve around the sun as per Kepler's laws of planetary motion. So let us discuss these three laws one by one. So let me write here Kepler's first law, or we also call it law of orbits. ठीक है ना? So this is law of orbits, or we simply call it the orbital rule, or simply Kepler's first law. Now what is the statement of this very law? As per Kepler's first law, every planet revolves around the sun in an elliptical orbit with sun at one of the foci of the ellipse. Now what is an ellipse? It is basically a closed curve. You can also see it here. Ellipse is basically a closed curve having two foci, This is foci f1 and f2. If I consider any point P on the ellipse, this is the special feature of an ellipse. This is f1p plus f2p always remains constant. And remember, dear students, circle is the special case of ellipse where a is equal to b. That is major axis, rather semi-major axis is equal to semi-minor axis. What is major axis? This axis is basically the major axis of the ellipse, and this is the minor axis of the ellipse. From this we call it the semi-major axis. So this will be the semi-minor axis. As per the Kepler's first law, every planet revolves around the sun. Let me consider the planet here. Every planet revolves around the sun in an elliptical orbit with sun at one of the focus of the ellipse. So this is sun at the focus of the ellipse and the planet revolving around it. Now the path followed by a planet, that is called the orbit. So Kepler's first law basically defines the path followed by a planet, that is the trajectory followed by a planet, and from the Kepler's law it is elliptical in nature. So the path followed by a planet around the sun is an ellipse. It is an elliptical path, right? Now when the planet is at the nearest point from the sun, this point is called perihelion. क्या कहते हैं हम इसको? Perihelion. When the planet is near to the sun, and when the planet is here, I mean at this very position far away from the sun, this position is called the aphelion. So let me write the terms here. This is aphelion. Now the path followed by a planet around the sun, it is basically ellipse and it is an elliptical path, and you now know, since this defines the nature of the orbit followed by nature of the path followed by a planet, that is why this is called the orbital rule or simply the law of orbits. This is the Kepler's first law. Now let us discuss Kepler's second law, that is called the law of areas. So let me write here Kepler's second law or law of areas. We also call it the areal rule, right? Now see, let me draw an ellipse here. This is the path followed by a planet around the sun. This is major axis of the ellipse. This is minor axis of the ellipse. This is focus f1 of the ellipse. Let this be focus f2 of the ellipse, and suppose S is here, I mean sun is here, situated at focus f1. Now as per the law of areas, let me tell you the statement of the law of areas. The line joining the sun and the planet, let the planet be at point A. The line joining the sun and the planet, and remember this is called the radius vector. So the statement will be the line joining the sun and the planet sweeps out equal areas in equal intervals of time. मैं आपको statement repeatedly मैं आपको statement एक बार फिर repeat करूंगा. The line joining the sun and the planet, it sweeps equal areas in equal intervals of time, or I can say the aerial velocity of the planet around the sun always remains constant. Now what does this mean? This is radius vector, that is the line joining the sun and the planet. Suppose the planet takes 1 month. Let me repeat it. Suppose the planet takes 1 month in moving from A to B, then it will sweep an area that is equal to the area of the sector. Let me name this S, that is the position of the sun. So this will be area of ASB, area of sector ASB. Now let me draw another sector here. Suppose this is position of the planet after some time, this is C and this is point D here. Now let me suppose that area of the sector CSD, it is, let me suppose here area of sector ASB, it is equal to area of sector CSD. Now as per the second law, the line joining the sun and the planet, that is radius vector, it sweeps equal areas in equal intervals of time. Now since the area of sector A as B, it is equal to the area of sector C as D. Now as per the second law, the planet must also take 1 month in going from C to D, because I have assumed it here. Suppose the planet takes 1 month in moving from A to B, then definitely if area of A as B, if area of sector A as B, it is equal to area of sector C as D, then the planet must take 1 month in moving from C to D. This is what Kepler's second law is all about. That is the aerial velocity of the planet. That is, let me write it here, dA by dt. This is aerial velocity of the planet around the sun always remains constant, and it follows from the law of conservation of angular momentum, which we basically discuss in 11th class. In 9th class, angular momentum is not in the syllabus. Basically this law, that is Kepler's second law or law of areas, it basically follows from the law of conservation of angular momentum. That is the aerial velocity of the planet around the sun remains constant. So if area of sector A as B is equal to area of sector C as D, then the planet takes 1 month in moving from A to B and again 1 month in moving from C to D. Now you can see from this very ellipse, or I have already drawn it here, you can see it from this very figure. Now you can see it, the ellipse, path followed by the planet. Now see here, the length of the arc AB, it is smaller than length of the arc CD, or conversely I can say, since the arc length CD, it is greater than AB, but the times of travel are same in moving from A to B and C to D, then how is it possible to cover equal area? Then the planet must move faster from C to D. I mean, the planet must move faster when it is closer to sun, so as to cover equal area in equal intervals of time. In other words, I can say the planet must move faster, that is the speed of the planet must be greater when it is closer to the sun and vice versa. So this is the statement of the second law. Simply the aerial velocity of the planet around the sun remains constant, or I can say the line joining the sun and the planet, it shapes equal areas in equal intervals of time. This is Kepler's second law, since it defines the aerial velocity that is constant for a planet because it follows from the law of conservation of angular momentum. So that is why this Kepler's second law is called the law of areas, or simply we call it the aerial rule. Now let us discuss the Kepler's third law, that is law of periods. So let me write here now Kepler's third law or law of periods. So this is law of periods, rather time period we define here, law of periods. Again I will draw an ellipse. If you can see this figure, this is an ellipse. Let me try to draw it here on the board. So this is an ellipse, that is path followed by the planet. Let me clear the terminology here. This is major axis, okay, this is minor axis of the ellipse. Then what can we call this axis? Semi major axis, and this axis as semi minor axis. Now if this is sun situated at one of the focus, this position will be called the perihelion, and when it is farther away from the sun, this position we call as aphelion. Now let me try to define the time period of a planet. Suppose the planet is here, let me call this point P. The time taken by the planet to complete one revolution around the sun, this is called the time period of a planet. Simply time taken to complete one revolution around the sun, that is called the time period of the planet, and you are already familiar with the time period of earth. याद है ना आपको कितना टाइम लगता है to complete one revolution around the sun, earth को? हाँ, it is equal to 1 year. 1 year. Okay, now this is time period. I have already defined it. Now this distance we usually call it R minimum, that is the distance of the sun from the perihelion, and the distance of the aphelion from the sun we call it R maximum. Now if I take the mean of two, that is R minimum, okay, plus R maximum divided by 2, we usually call it the mean distance of the planet from the sun. क्या याद रखा आपने अभी तक? I defined the time period of a planet around the sun, and the average distance of the planet from the sun, usually called as, in simple language we call it the semi-major axis. We assume it to be the semi-major axis. Now we simply denote it by r. There is a relation between the time period and r. Either you can call this as semi-major axis, or you can call it the average distance of the planet from the sun. Okay, the relation is given by law of periods. क्या है इसका statement, मैं यहाँ पे बताऊंगा आपको. T square is directly proportional to r cube. I mean, according to Kepler's third law, the square of the time period of a planet around the sun, it is directly proportional to cube of the semi-major axis of the elliptical orbit, or you can say cube of the average distance of the planet from the sun. This is the statement of Kepler's third law. So I can write here T square is directly proportional to r cube. Now to replace this sign of proportionality into equality, as usual in physics, we introduce the constant. So let me write it k. So this is equal to k into r cube, or I will write T square by r cube, it is equal to constant, right? Now this is basically the Kepler's third law, that is T square by r cube for all planets is constant. Now you can see from this very law, smaller the orbits of the planets around the sun, shorter will be the time taken by the planet around the sun. You can also see it from this very figure, you can also see it from that very diagram. Smaller the orbits of the planets around the sun, shorter will be the time taken by the planets around the sun, and vice versa. Now you need not to remember the value of this constant k here, because we usually compare the time periods and the average distance of the planet with respect to some other planet, usually Earth. So if I consider T1 and T2 to be the time periods of two planets around the sun, and suppose R1 and R2 are their, you can say, semi-major axes, or you can simply say their average distances from the sun. So as per this very law, I will write T1 square is equal to k into R1 cube, और मैं लिखूंगा T2 square is equal to k into R2 cube. Now if I divide first by second, this is first, this is second. So let me divide first by second, or you can simply say dividing second by first. I will get T2 square by T1 square, it is equal to R1 cube divided by R2 cube. क्योंकि k और k constant हो जाएगा, इसलिए मैंने कहा था आपको you need not remember the value of k here. Now by using simple mathematics, I will write this third law here. Simple mathematics I will use. So I will get this is T2 by T1 whole square, it is equal to R2 by R1 whole cube, or simply I will write T2 by T1, it is equal to R2 by R1 whole raised to the power 3 by 2. This is the relation between the time periods of the two planets and their respective distances from, and the respective distances of the planets from the sun. So T2 by T1 is equal to R2 by R1 whole raised to the power 3 by 2. So you can find, you can compare, basically this is basically the third law, Kepler's third law. You can compare the time periods and the respective distances of the planets from this very mathematical form of the third law. So this is Kepler's third law, also called the law of periods, that is the square of the time period of a planet, it is directly proportional to cube of the average distance of the planet from the sun. Now let us apply this very law to Earth Sun system so as to remember the value of k for Earth Sun system. So let me consider here Earth. Okay, this is sun. Do you remember the average distance between Earth and sun? याद है ना आपको, मैंने ही पढ़ाया था आपको, average distance between Earth and sun, it is equal to 1 astronomical unit, that is equal to 1.5 into 10 raised power 11 meter. This is the average distance between Earth and sun. By the way, what is the time taken by the Earth to complete one revolution around the sun? अभी मैंने आपको बताया T is equal to 1 year. ठीक है ना? Okay. Now, as per Kepler's third law, T square is equal to K into R cube. Let us try to find out the value of K for Earth Sun system. Okay, T square के बदले क्या लिखूंगा 1 year square, ठीक है ना. Okay, so this is equal to K R cube के बदले लिखूंगा 1 astronomical unit whole cube. You can also convert it into SI system. So the value of K can be expressed as 1 year square divided by 1 astronomical unit whole cube. Now you know 1 year is basically equal to 365.25 days, or you can simply say 365 days. Then you know how to convert days into seconds. Can you do this? Yes, this is an assignment to you people. How many seconds are there in 1 year? Let me elaborate. How many seconds are there in 1 day? 1 day is equal to 24 hours. In 1 hour there are 60 minutes, and in 1 minute there are 60 seconds. You can see this is 86400 seconds. So 86400 seconds are there in 1 day. Simply you have to multiply this by 365. You will get the number of seconds in a day, because the SI unit of time is second. And I have already converted astronomical unit into meter. This is 1.5 into 10 raised power 11 meter. And for the Earth Sun system, the value of K in SI is 3 into 10 raised power minus 19. Unit will be second square per meter cube. You can also see it from the diagram. This is for Earth Sun system. K is equal to 3 into 10 raised power minus 19 second square per meter cube. So these were the Kepler's laws of planetary motion: law of orbits, law of areas, and law of planets. Law of periods. That is the time relation between the time period of the planet and the average distance of the planet from the sun. Now let us try to solve one question regarding the Kepler's third law. Let me read the question here. Okay. Earth completes one revolution around the sun in 1 year. You already know it. If the distance between them becomes double, the new period of revolution will be. Now as per the second law, अभी मैंने आपको बताया T2 by T1 it is equal to R2 by R1 whole raised to the power 3 by 2. You are getting my point or not? The distance between them becomes doubled. What will be the new period of revolution? So T2 is equal to T1. Okay, R2 के बदले लिखूंगा twice R1 divided by R1 whole raised to the power 3 by 2. R1 और R1 cancel हो जाएगा. So this is T1 into 2 raised power 3 by 2. क्या मैं इसको ऐसे भी लिख सकता हूँ 2 cube whole raised to the power 1 by 2. Yes, I can write it. T1 is equal to 1 here. 2 cube is equal to 8. So this is 8 raised to the power 1 by 2. What is square root of 8? I can write this in simplified form. So this is 2 root 2 years. You got it or not? I mean, if the distance between them, if the distance between Earth and Sun is doubled, the new period of revolution will be 2 root 2 years. You can substitute for root 2 1.414 multiplied by 2. You will get the number of years the Earth will take if the distance between Earth and Sun becomes doubled. So these were Kepler's laws of planetary motion, the historical background of the planetary motion, and the 3 laws of the Kepler, and some of the numericals regarding the third law, that is Kepler's third law. Hope you enjoyed today's lecture.